And actually, today I'm feeling a little bit redundant because to present David Grinspoon might be a little bit redundant because most of you will have met or will have had some conversation with David. Um, David is not only an astrobiologist, he's also authored many books in the field, and he's now at the Planetary Science Institute, but was also involved with several interdisciplinary, interplanetary spacecraft missions for NASA, ESA, and also JAXA, the Japanese Space Agency. Very importantly, he was appointed as the inaugural chair of astrobiology at the US Library of Congress, sorry, and where he studied the human impact of Earth system. And he has also organized several symposia in the field. He has been recipient of the Carl Sagan Medal for Public Communication of Planetary Science, so he does also a lot of public engagement work, amongst many other awards. If you know David a little bit better, you will have noticed that he's also a keen musician and takes a very great interest into modern music of all kind. And he actually leads a band which is called the House Band of the Universe. So talking about a broad ambition of these musical efforts also. Now, I think I have talked enough, and I would like to thank David for joining us for the first seminar in 2026 and leave over the floor to David. Many thanks for coming, and many thanks to you for attending this seminar.
Okay, thank you very much, Wolf, and thanks to all of you for attending. I would say good morning, but good afternoon in Europe, and good day from whatever planet you happen to be joining us from. I actually am not where I had intended to be, which was my home institution, well, which is now in Washington, D.C., but you may have heard we had a massive snowstorm and I got stuck in Boston. So I'm now hiding out at my brother's house outside of Boston. But he happens to have a video studio in his house, which is why I have a nice green screen behind me. So, okay, I want to talk about the astrobiological potential of Venus. And the first thing I want to point out is that this is not the same as the as the biological potential of Venus. It's not necessary that Venus ever had life to have Venus be a very important, and I would say central location of astrobiological study. The possibilities, of course, are many, but some of the most obvious possibilities are that Venus never had life. Venus may have had early life, which died out when conditions changed if it lost early oceans. Or there's this other strange exotic possibility that maybe there's life today in the clouds as a sort of escape from the surface conditions, which became uninhabitable at one point. And all three possibilities have very important implications for life in the universe. So in broad strokes, Venus holds clues for us about how stable habitability may be in our solar system and beyond. Venus gives us a sort of ground truth when we want to study exoplanets. It's been called the exoplanet next door because we can actually study it up close and learn perhaps better how to contextualize the limited observations that we have from many exoplanets. And of course, it helps inform how our understanding of stellar evolution governs climate. And all of these are true whether or not Venus ever had life or for how long Venus may have had life. There's also this exotic possibility, as I mentioned, of cloud-based life today, which I'll talk about at least a little bit. So there's a long history, of course, of interest in the question of life on Venus. And through much of certainly the 20th century before the space age, it was widely believed that Venus was a somewhat Earth-like place and perhaps a promising place for life. And some very esteemed scientist here, Professor Eddington, Arthur Eddington, is being quoted in the New York Times in 1928 talking about how Venus is perhaps an ideal place for life because it's the same size as Earth, nearer the sun, but probably not warmer, an atmosphere, and so forth. And so, why not? And this, of course, led to a lot of great science fiction literature. One of my favorite books when I was a kid was Isaac Asimov, Lucky Star and the Oceans of Venus, where our hero Lucky battled giant jellyfish and telepathic frogs to fight the bad guys underneath the oceans of Venus. And the first ever planetary exploration, successful planetary exploration, of course, the first ever successful mission to another planet was Mariner 2 in 1962. And it carried this microwave photometer, which successfully determined that the source of the anomalous microwave radiation from Venus was not the high atmosphere, as some had proposed, but was the surface, which meant that Venus had to be very, very hot and not at all a place where you could have liquid water or organic life. And this was widely seen as a big disappointment. And this is the editorial in the New York Times from right after these findings were reported, and you can see that it says here, one all-important question remained unanswered, whether or not life in some form existed on Venus. And the answer is a disheartening, disillusioning no, not on Venus. The high temperature definitely rules out the possibility of life in any form, even remotely resembling life on Earth. The finding of extraterrestrial life in some form would lend support to the widespread belief rooted deeply in the aspirations of mankind that life as we know it is not unique to this insignificant corner of the universe. And then the end here, it says, Mars now remains our only hope of turning this universal dream into reality. The message from Venus may mark the beginning of the end of mankind's grand romantic dreams. So that's a pretty strong statement of disappointment. And that was sort of set the stage for later exploration. And one of the astounding findings when we began to really understand the difference between Venus and Earth with both remote observations and later entry probes by both the Soviet Union and the US was the extreme lack of water on Venus compared to Earth. On Venus, there's in terms of column density, there's 3 centimeters equivalent of condensed water in the atmosphere, and of course, none on the surface. Interestingly, Earth has about the same amount in its atmosphere on average, about 3 centimeters equivalent. So the atmosphere of Earth on average holds about the same amount of water as the atmosphere of Venus. But of course, there's 5 orders of magnitude more water on Earth condensed on the surface. So it's a very extreme difference. And we've, in very general terms, understood that as the result of a runaway greenhouse early on, perhaps in the planet's history, and then a little more modeling led to the idea of a moist greenhouse, which is basically when you have the atmosphere really saturated with water, and the idea is you can still have condensed water on the surface when a lot of the escape is happening. But at any rate, the idea was it was widely believed for a long time that Venus probably lost basically all of its surface water very early on. But these models were very crude because they were one-dimensional, and very importantly, they didn't include the existence of clouds or the feedback properties of clouds, which can be very powerful in determining climate evolution. The early models by Casting and others, they basically just assumed a planetary albedo. They sort of painted some amount of clouds on the surface and left it that way. And there's a reason for that. Clouds are very difficult to model, and you really can't do it with these one-dimensional models. So we were left with the question, did Venus have oceans? There was no direct evidence of past oceans, but a lot of sort of circumstantial reasons to believe. Of course, as I'll talk a bit more, the deuterium-to-hydrogen ratio implies that most of the water that was originally there somehow is gone. Extreme amount of escape for that extreme fractionation. It doesn't prove there was surface water. Formation models suggest Venus must have had surely much more water than today. It's very hard to create two planets next door with such an extreme difference in water abundance, given what we know is the sort of chaotic and random stochastic nature of planetary accretion. There's sort of an Occam's razor argument. You don't make one planet completely dry and one planet completely wet right next door. There are other arguments based on formation models and so forth, and climate models mostly suggest that with a faint young sun, Venus would have had liquid water on the surface, but that does depend on some still unknown factors. And there's the possibility that early solar activity could have prevented surface water condensation and removed most of the hydrogen and water without surface oceans. So that still remains possible given the poor quality of the observations we have today. A major advancement in understanding the nature and evolution of Venus, of course, was the Magellan mission in the early 1990s, which laid bare the surface of Venus to us with radar imaging. And it became very clear early in the Magellan mission that the surface of Venus was not ancient, was mostly covered by plains with an average age of something like 500 million years or less than 1 billion years. And so the surface history of Venus, the resurfacing history, is still somewhat in dispute, but it's clear that we're not looking at an ancient primordial surface, but a surface that's been almost fully resurfaced one way or another in the last billion years. And if you look at this sort of cartoon of comparative planetary history that Jim Head made, you can see that, for instance, most rocky planets that we know of in the solar system, the Moon, Mercury, Mars, have surfaces that are dominated by very ancient processes. That if you pick up a random rock on Mercury or Mars, it's going to be billions of years old. In contrast, if you pick up a random rock on Earth, it would be very, very strange if it was more than 1 billion years old. It's going to be much younger than that. And in that general sense, Venus is like Earth in that most of its surface is not ancient, but is, in that geologic sense, relatively recent. Now, you see the question marks around the shape of Venus because we really don't know, and there's still debate about when exactly all that resurfacing or most of that resurfacing happened. But it's clear that in this overall sense, Venus has a young and probably active surface, which puts it in a category with Earth and different from all other rocky planets in our solar system. Learning this, and this happened to be for me around when I was doing a postdoc and starting my first faculty job and so forth, that I with some colleagues, put together a Venus climate model because we really wanted to understand the interactions between the geological and the atmospheric history, realizing that Venus had a complex and active resurfacing history, and realizing that that meant a lot of outgassing and a lot of interesting and complex feedbacks between climate and surface chemistry and outgassing and cloud chemistry and formation and in turn effect on the radiative balance of changing clouds and so forth. We wanted to try to capture all this in a model, time-stepping model that had, as you can see on the left here, modules for outgassing and photochemistry and cloud formation and so forth. And through this, we were able to identify a lot of interesting processes and feedbacks, and we published a series of papers. And what I'll say about those papers is that they're our papers about the recent climate evolution on Venus is that they're surely wrong in the details because we had to assume a lot for these models. But I think we were successful in identifying a lot of important feedbacks and important sort of areas that were needed to be studied further to understand all the complex interactions between clouds and the atmosphere and the surface and the interior. And the intriguing thing that's been studied more recently is how some of these thermal changes on the surface propagate into the interior and in turn can feed back geodynamically with outgassing and resurfacing and so forth. So Venus is a complex place, and that makes it interesting and also very hard to figure out. And one question we started to wonder about was, did Venus experience one great transition or two? What do we mean by that? Well, there's the loss of oceans, and then there's apparently this change that happened that led the surface to be relatively young, meaning less than 1 billion years old, which some people have called a global resurfacing event. There's been a lot of debate about whether it should be called a global resurfacing, so I'll just say it doesn't matter, but at least there was some dramatic change in resurfacing style and rate. It's not been steady since over the history of the planet. And so there's some kind of transition that happened with the interior or the surface. And the interesting thing is, are those really two separate transitions? One that happened early with the loss of oceans and one that happened more recently with a change in surface resurfacing dynamics, or could they be part of one causal sequence? And I wrote about this a little bit way back in the early 2000s. And one thing I pointed out, and this is with my colleague Mark Bullock and others, was that if the drying out of the surface was delayed enough, you can imagine that drying out propagating into the interior through some kind of recycling mechanism, and in turn that desiccating, that drying of the interior, leading to these changes that we see on the surface. With drying out of the interior, cessation of plate tectonics, and then dramatic changes in the resurfacing history. So it could all be part of one sequence. But what would delay the loss of the oceans? And you can see what I've highlighted here that I wrote back in 2003. If clouds stabilized the moist greenhouse and the Venus oceans persisted for several billion years, rather than hundreds of millions, as was believed then the loss of water could have initiated these changes in convective style and so forth. But that's a big if clouds stabilize the moist greenhouse. We did some experiments with some 1D models where we tried to incorporate the effect of clouds, and we found that it did, in fact, delay the loss of water, but it was these were very crude experiments. But more recently, the group led by Mike Way at GISS has been able to successfully apply a 3D model using the Rocky 3D model, an actual Earth-style GCM to Venus, and sort of properly model this question of the changing climate on Venus with the loss of water and the changes to clouds. And what they found is very interesting, that for a slow rotating planet like Venus, and that's very important here, that in this situation, the clouds organize themselves in an unusual way so that the sun-facing side of the planet is cloudy and the night-facing side of the planet is permanently clear. And as you can see in the lower left, this cartoon I've drawn here, that means that the clouds sort of act as a sun shield and the night side acts as an efficient radiator without clouds. And that helps to keep the planet cool, perhaps for billions of years. And so we had this very provocative paper: was Venus the first habitable world of our solar system? And you can see I've highlighted here the in the abstract, Venus's climate could have remained habitable until less than a billion years ago. Um, which is an exciting possibility. Now, there's a lot of caveats in here, and there's assumptions in the models that still need to be borne out. And of course, our future exploration will help there. But if you just ponder what this could mean, and you think about what was happening on Earth during all those billions of years, that there may have been a habitable oceanic planet right next door. You think about, the origin of life on Earth and the beginning of life, and even complex photosynthetic life. All these things happening on Earth during that time, and if you also consider that life could have been transferred between the planets through the mechanism that we know about of occasional impacts and meteorites transferring material, then it's just exciting to think that maybe there were, for much of our solar system's history, there may have been these two Earth-sized oceanic planets right next door, perhaps even exchanging material, and who knows, exchanging organisms. So it's a very provocative image. And one thing it tells us is that the habitable zone is a lot more complicated than we thought, because this has been modeled and you've seen these kinds of models, but it may not be that there's one line of the interior of the habitable zone. It may depend on a lot of things, including rotation rate. The idea here, these models suggest that for slow rotators, the inner edge of the habitable zone might be quite a bit closer to the star. And even planets that are not drawn in the habitable zone on a chart like this may have had oceans for hundreds of millions of years before they lost them. I mean, this is really a chart of really the sort of end state, but you could even have what I've called sort of meta-habitability. If it takes hundreds of millions or even billions of years to lose your ocean, even if you're not in the habitable zone, you may have an ocean for a long time. So this led me, this is an essay I wrote in Sky and Telescope several years ago about life outside the habitable zone. But the point here that I've got in yellow is I think that we have to consider worlds that are sort of meta-habitable, an analogy to metastable chemistry, that if oceans can persist for billions of years, even if they're not in the habitable zone, then that could be plenty of time for life to happen. And you see, I put on the bottom here, you think about a system like TRAPPIST-1 with perhaps multiple rocky planets. And even if they're not all in the sort of long-term habitable zone, if some of them have oceanic phases that last for hundreds of millions or billions of years, you can imagine life potentially sort of hopping from one promising world to the next. So this does complicate things in an interesting way. But just to caution us here and not get too carried away, other studies suggest Venus may have never become habitable, because there are some suggestions that Venus never had an ocean because of early solar extreme ultraviolet radiation, and because of various feedbacks of stratospheric clouds and so forth. I don't have time to get into all of this, but I would say it's still an open question whether for sure Venus had condensed water. But if it did have condensed water, there's reasons to believe that it may not have been lost very quickly, and could have even potentially persisted for much of the planet's history. Now, how can we study that? One way is through the deuterium-to-hydrogen ratio, of course, and this is something I've worked on a lot over the years, and it's something that Da Vinci will measure very precisely and at many altitudes, which is great because there's some uncertainty about the altitude distribution, not just the abundance of deuterium on Venus. And so hopefully with upcoming missions, we can really nail that down. And that's an important diagnostic clue. And this is something I wrote way back in the Pleistocene age in the 1990s when I was, fresh out of grad school. But it's a problem I've been studying for a long time. But this was just post Magellan, and when it was the idea of volcanic outgassing seemed very likely. And so One of the points of this paper was that water on Venus is probably in a steady state with the volcanic outgassing. If you look at the lifetime, given the what was then the estimated escape flux and the estimated water abundance, the lifetimes are long enough so that you probably are in steady state with the volcanic outgassing. And that means that rather than reflecting a primordial water abundance, it might reflect more recent steady state processes, or at least those processes have to be included in the modeling. You can't just assume it's a residue of primordial water. It could be the residue from massive water loss more recently in the last billion years. Interestingly, it also implies that the outgassing flux is a measure of magma water abundance. So if you think you know the outgassing flux and you think you know or you can constrain the resurfacing rate, then you know how much water is in those magmas, which is interesting for a lot of reasons. But it's also very hard to reconcile the current low water abundance with relatively recent oceans. Given the current escape flux measurements, the escape flux isn't high enough to get rid of all that water in a short amount of time. So that's a bit of a puzzle. Now, more recently, also, well, yes, more recently, Venus Express, very importantly, found a lot of circumstantial but pretty compelling evidence for recent volcanism on Venus. This is Sue Smirkar's famous paper, Smirkar et al., showing emissivity patterns that suggest that the fresher volcanoes have not equilibrated with the atmosphere, and therefore there may be recent volcanism. And more recently, Herrick and Hensley reanalyzed some Magellan data, and they even found that over the period of something like over a period of just months, I think eight months, well, something close to a year, between passes of Magellan, that you can see over on the right here, this vent, this down in the lower right, this expanded vent. It's noticeably different in shape between these two Magellan passes. And that suggests, in fact, active volcanism during the Magellan mission. Now, there's some questions about viewing angle and so forth, but still, all of this is adding up to more and more support for the idea of active volcanism on Venus. So there's a problem, though, as I mentioned, which is how do you get rid of enough water if you want to reconcile the low water abundance today with the possibility of more recent oceans, because the loss rates just aren't high enough. But there's some recent work. This came out last year in Nature by Mike Chaffin and colleagues, suggesting that there's a very important loss process for water on Venus that's been overlooked. HCO plus dissociative recombination. I won't go into detail about the mechanism, but before this, we believed that sort of hot hydrogen loss through well, anyways, there are other non-thermal mechanisms that have been studied for a long time, but this had been an overlooked mechanism that Chaffin and colleagues calculated is twice as effective as the other known mechanisms. In other words, we may have been underestimating the escape flux from Venus by a factor of 2 by neglecting this mechanism. And that means that it is possible maybe to reconcile the current water abundance with relatively recent oceans. You can see over on the right here, if you look at that sort of red curve over on the right, that the published loss rates were not high enough to explain the dry atmosphere if there was water on the surface just a billion or 2 billion years ago. But if you include this new loss process and the greater rate of loss of hydrogen, then it starts to become more conceivable that you can reconcile all the observations. So this is exciting, and it's preliminary. And one thing that emerged from this is that we really still don't understand hydrogen loss very well. And Mike Chaffin has argued, I think, had advocated, I think, in a compelling way, that it would be great to have a future mission on Venus, sort of like the MAVEN mission on Mars, which is specifically looking at understanding the upper atmosphere and loss processes, which is something that unfortunately none of the three planned missions of Venus are going to do. They're going to do a lot of important work, but none of them are going to really focus on these upper atmosphere processes. So, at any rate, this is looking like maybe more promising to reconcile these sort of discordant ideas. It still leaves us trying to understand the D to H ratio. And again, that's something that we need to do a lot more modeling of to understand what the real fractionation factors would be for these different escape mechanisms. So clearly, Venus and Earth had some kind of divergence. But when? Was it before the oceans even had a chance to condense? Was it due to a moist greenhouse early of a condensed ocean, or on what timescale might that have happened? And the various observational tests we can do with our upcoming missions, including the rare gases, the heavy rare gases especially help us to constrain the outgassing in early escape history. The D to H ratio I've already mentioned. Other isotopes, helium might help us to constrain different sort of timescale of escape. And then importantly, the surface composition. Are the tessera felsic? And if they are, then that may be a clue to them being remnant continents, which would have had to form in a more water-rich environment. And even geomorphology with the upcoming missions. Do we see ancient sediments? Do we see shorelines? Now I want to switch gears for a few minutes and talk about this possibility I mentioned of extant life in the clouds. The idea being that if you look at the temperature and pressure in the middle clouds, they're pretty much the temperature and pressure that of our current environment. Maybe not right here where I am now because it's very cold out, but in general, it's sort of an Earth-like temperature and pressure in the middle cloud range of Venus. This has led some of us for a long time to propose the possibility of a habitable zone up there. And we've pointed out that the global clouds are larger and more continuous and more stable than clouds on Earth, with particle lifetimes of months or even longer in some realms. That the mode 3 particles, which make up the bulk of the cloud layer, seem to contain unknown absorbing core material, which may in fact be most of the volume and the mass of the cloud particles, may be something that we don't know or haven't characterized, coated by sulfuric acid. And there's a lot of interesting chemical disequilibrium in the cloud region with hydrogen and oxygen and various sulfur gases, which, potentially could be a source of some kind of metabolic energy. And of course, there's abundant solar energy as well. There's also this what's known as the unknown ultraviolet absorber, which is mostly in the upper cloud layers. And whatever it is, it absorbs a ton of solar energy, more than half the solar energy striking Venus. We don't know what it is. It's been proposed to maybe be compounds of sulfur or chlorine. More recently, Jan Spacek and colleagues have proposed that it could be some kind of organic compound that's actually stable in the upper atmosphere of Venus. They have some experiments they've published which support this very interesting idea that needs to be examined further. And it's been proposed by myself and by others that at least conceivable that could be some kind of biological pigment. It absorbs in a very unusual way. It hasn't been characterized, and it's harvesting a lot of energy. It doesn't mean it's harvesting it for biology, but who knows? It's an interesting possibility at least. Now, thinking about the history of how this could work during an extended period of water loss, Venus, I would point out, probably had an oxygenated atmosphere, which is maybe neither here nor there, but kind of interesting because as hydrogen's being lost, oxygen builds up and then escapes more slowly. The young planets were exchanging material. And as surface conditions became hostile, the question is, could life have adapted to an atmospheric niche under directional selection? And Dirk Schultz, Makuch, and I, and some other colleagues published an idea, sort of a thought experiment of the role sulfur could play. Sulfur on Earth acts as a very powerful sunscreen for ultraviolet radiation and can even sort of harvest ultraviolet radiation for some organisms. And so that's it's sort of the idea of it being used as an energy converting pigment was something that we sort of had some fun speculating about. And Sarah Seeger, as you've probably seen, has proposed, and her colleagues have proposed this very clever life cycle for possible Venus life, where the subcloud haze, which again is uncharacterized, could potentially be spores, which are then lofted up through convection and form new cloud uh, cloud organisms, which then reproduce and form more spores, which fall out. And again, all of this is very speculative, and I wouldn't I wouldn't put money on finding life on Venus, but I would regard it as a possibility that is cannot be ruled out and is one of many reasons why the clouds of Venus need to be explored. And it's also, in terms of thinking of astrobiology more general, whether or not there's cloud life on Venus, the idea of cloud life somewhere, including on exoplanets, is something that ought to be explored because arguably there are cloud environments that have everything that we know of that is required for life. And so it ought to be within the discussion of possible habitable niches. Now that there's arguments about the low water activity in the clouds and the extreme acidity, and these are challenges to life as we know it. But one thing we also know about life is that it seems to have a way to overcome challenges due to necessity. So who knows? But I would point out that that all ideas about extraterrestrial biochemistry are extrapolations from one single example. So we have to remain humble and resist sort of groupthink. Like we all really know where's a good place to look for life and where's not. Let's admit that we need to explore broadly because we don't know enough. We don't know much about life in the universe, and it's certainly plausible that life exists within the ocean of an ice-covered world that has never seen sunlight, like Europa. It is certainly plausible that life exists underground within a planet that is largely geologically dead, like Mars. And it is plausible that life exists within the clouds of a planet with vibrant chemical flows, energy sources, stable aqueous environment, and so forth. So, in my opinion, among the plausible niches for extraterrestrial life in our solar system, the clouds of Venus are among the most accessible and the least well explored. Now, another interesting thought about Venus and the value of studying it is that it could give us insights into the future of life. This is actually a workshop we put on last year at the Lunar and Planetary Institute on astrobiology and the future of life. It was a really fun and interesting meeting, and one topic that came up is the question: is Venus a possible endpoint for Earth habitability? This is actually something I'd written also about before in one of my Sky and Telescope essays, that for both Venus and Earth, life's last refuge might be in the clouds. And I pointed out that Venus could represent an end state for Earth in terms of climate and in terms of geology and in terms of biology. Ultimately, there probably will be some kind of a runaway greenhouse on Earth billions of years in the future, of the kind that probably happened on Venus in the past. And if that on Venus, that did drive the changes in the interior, the desiccation of the interior that led to the cessation of plate tectonics, then that's a plausible end state for plate tectonics on Earth as well. And if life on a dying oceanic world can migrate to the clouds, as might have taken place on Venus, then that might be the long-term fate of Earth's biosphere. So the clouds may be our planet's final habitable zone. Something just fun and interesting to think about. So the last point I want to make in just my last few minutes is about sort of some general properties of biospheres and something we've learned about Earth that we ought to apply when we think about other planets. That on Earth, we've learned that life is a planetary scale process and that environments and ecosystems co-evolve. So it's not enough to just have a planet that's designed in a habitable way and sprinkle in some life and then life exists. No, life interacts with and feeds back and controls ultimately the habitability of a planet. And over on the left here, you can see some of the changes on Earth and the feedbacks between environment and life of some of the obvious ones: oxygenic photosynthesis, And there have been a lot of long-term interactions in the coevolution between life and the environment. And this has also led us over on the right here to realize that when we think about exoplanets, that we can use Earth to model not just the spectral signature of a modern Earth habitable signature, but also we know enough, we think about the Proterozoic Earth and the Archean Earth to model their spectra. And we couldn't do that without starting to really understand this coevolution of life and environment. The methane on the Archean Earth is probably a product of biology and so forth, and the oxygen on our modern Earth is a product of biology. So I'm going to skip through this pretty quickly, but there's just some alternate ideas about life. We tend to often think about defining life, in this very micro way of a self-perpetuating chemical process that evolves through Darwinian evolution. But you can also think of it as the property of a system, and this is the idea of living systems theories. And I won't go through all of this, but just on the bottom, you've of course heard about the Gaia hypothesis, which regards life as a planetary property, proposed in the 60s by Lovelock, first by Lovelock and Margulis in the 60s, and elaborated in the 70s in this famous paper, Atmospheric Homeostasis by and for the Biosphere. And my colleague Colin Goldblatt has summed this up by saying the defining characteristic of Earth is planetary scale life. And Earth teaches us that habitability and inhabitants are inseparable. And I've, in some of my writing, expanded on this a little bit in what I call the living worlds hypothesis. And the idea is that, sort of highlighted in yellow here, that life is not just something that sometimes happens on a planet. Life is something that happens to a planet. It's a change in state of the planet, perhaps, not just something that is sort of a condiment on the meal. It is the meal, if you will. And if you view it that way, then long-term habitability may depend more on the establishment of a robust and resourceful global living system than on just having a lucky planet and a lucky star. This idea has also been explored in a similar way by Chopra and Lineweaver in what they call the Gaian bottleneck, that you may have planets that are inhabited early on, and then a lot of them may die out if they do not succeed in establishing a global set of feedback loops between the biosphere and the rest of the planet in a way that supports robust continuity. And that's the idea of the Gaian bottleneck, that maybe establishing a self-reinforcing biosphere is important for long-term inhabitants of a planet. And, it's worth pointing out that life on Earth exists at the interface between two powerful and permanent convective heat engines, the interior convective engine and the exterior convective engine driven by sunlight. And if you look at the lower right here, I won't go through all of this, but so much of what keeps Earth habitable has to do with the interaction between these two heat engines. And so we can ask, maybe this isn't just lucky, but maybe this is actually a condition for a biosphere. And where else in the solar system is this condition met? I would say two places, Titan and Venus. We could argue this, but Venus has this quality, we think, of interior activity and exterior convecting atmosphere. And that is, it's just interesting that those properties seem essential to life on Earth. And they're not met a lot of places, but they are met a few places that we know. So this is what I call rare properties of astrobiological interest, Venus being our only other example of an Earth-sized terrestrial planet, a currently active terrestrial planet. And so if we think beyond the specifics of a particular chemical system required to build complexity and heredity and ask what general properties an inhabited planet must possess, then we are drawn to the idea of chemical disequilibrium, solar-driven chemical and dynamical cycles, and active internally driven cycling of volatile elements between the surface, atmosphere, and interior. And at present, the two planets we know of which possess these characteristics are Earth and Venus. So this is just another argument for understanding what's happening on Venus, even if just to satisfy ourselves there's no life there and become more sophisticated at ruling out false positives when we study exoplanets. Um, okay, one last point because I want to leave time for questions. But we've had these flagship mission studies um, in the last decade, a couple of them, and we didn't get our flagship mission, but we did get, we think, hopefully, fingers crossed, three really good Venus missions, which arguably add up to almost a flagship mission. And if you look at the combined observations we're going to be able to make with Da Vinci and Veritas and Envision, you can almost regard it as a collective flagship mission. Um, and I'm going to skip this. This is just about how the different missions can help us to study water history on Venus. But I just want to end with a point I made, and this is from a talk actually I gave about Europa Clipper, but I think it's applicable here, that in order to study habitability, it requires a systems level approach because habitability is an emergent property of a complex system, and you can't study it with one instrument or one experiment. That life is a planetary scale, at least over on the right here. If on the one inhabited planet we've studied, life is a planetary scale property, which has deeply altered most of the planetary properties that we can observe. Understanding habitability requires a systems approach. And this is from a paper Bob Papalardo wrote about the philosophy of Clipper that I really liked, that in order to achieve the goal of exploring Europa to understand habitability, then we must step beyond the comfort zone of our own specific scientific disciplines and work across the instrument realms. And so they've adopted this one team philosophy where, as much as possible, they get the different teams to talk to each other. And I think that in a certain sense, as a Venus astrobiology community, even though we have these three upcoming missions, which fingers crossed are all going to still happen. That's another whole topic. But as of today, they're all alive in one way or another. Then we really need to adopt this sort of one team philosophy and treat them in a certain way as a combined flagship mission, and that's the way that we will be able to assess the past and present habitability of Venus and the implications of Venus's state and evolution for habitability in the universe, regardless of what's happened on Venus in terms of life. Because ultimately, the assessment of whether or not a planet is habitable will need to be embedded in the context of the outcomes of terrestrial planet evolution. And I think I'll stop there. Thank you very much.
Thank you so much, David. So the floor is now open for questions. So I think I saw one already in the chat, actually two. So David, I will just read them and then you can answer. So first question from Camille. How does habitability differ from durability in the context of astrobiology?
Mm, Interesting question. Um, so I guess as I understand it, irritability, is that the right word? Is the probability of the origin of life. Please tell me if I'm wrong, as habitability is the probability of supporting life over the long term. So obviously they're related, but they're not the same. One can imagine, maybe one of the challenges of long-term habitability is making the transition from one to the other, because it's very clear, for instance, that that Earth today is habitable, but is not a good place probably for the origin of life to occur naturally with all this annoying oxygen that would interfere with sort of indigenous organic evolution. So, as far as the context of astrobiological exploration, it's a good question. I think it requires us to widen our view screen in a sense, and that, like, when we're looking at exoplanets, don't just look for the signs of life, like oxygen is a great sign of life, but it's probably not a great sign of this other quality where of the potential for origin of life. So I think it requires us, again, if you go back to that plot I showed of the different spectra of the different time periods of Earth, we can even imagine an earlier one when life was just getting formed. And maybe we should do some modeling of that. What would the spectra of that planet be, and how would that differ from even an inhabited planet? So I don't have a more sophisticated answer right now, but I think it's a worthwhile question for us to think about.
Thanks. We have another question from Sergey. What is known about the density of Venus' atmosphere over time? I've heard that Venus would have an habitable temperature if its atmosphere were less dense. Can we expect it to become habitable in the future when Venus loses most of its atmosphere? Could density also influence the rate of water loss in the past?
Yeah. So what do we know about the history of the density of the atmosphere? The one thing we do know that, could be considered a solid observational constraint is that when you look at the Magellan images, you don't see any craters that are smaller than about 4 kilometers. And that is consistent with the current density of the atmosphere of about 90 bars at the surface. If you do this is a problem I used to make my atmospheric science students solve, which is that if you have an atmosphere of a certain density, you can calculate the smallest um, object that will not be stopped by the atmosphere. Smaller objects will be stopped and will not make a crater. Bigger objects don't see the atmosphere. And it's a pretty simple, good student calculation if you just equate the mass density of atmosphere that an object will encounter with the density of the mass, you can get a pretty good heuristic answer. And the answer for 90 bars is about 4 kilometers, and that's what we see. So that tells us that over the lifetime of the visible surface, which is maybe something like 1 billion years, um, you don't see smaller craters, so the atmosphere has been the same density. Now, people have tried looking in the tessera because the tessera are probably the much older areas of the surface of Venus. And so it would be very interesting if the tessera were full of smaller craters. That might tell you, oh, the atmosphere was thinner in the past. You don't see that, but it's also harder to sort of determine that because the tessera is a smaller area and they're very, very tectonically disrupted, rugged areas. So it's not as easy to count craters as it is on the plains. But we don't see any obvious evidence in that data set that the atmospheric density has changed. Certainly, it could have in the past, and I think that's something to remember when we're doing these evolutionary models, that we can't yet assume we know enough about the history of the atmosphere to just assume that's been constant. I think that's the kind of thing that with the Da Vinci measurements of the rare gases and constraints on outgassing and loss processes, we will become more confident over time. But as of now, all I can say is that the best data we have suggests that that is a property that at least has gone back 1 billion years and probably farther.
A question from Oleg. Can life survive not only in the clouds, but also in deep subsurface ecosystems?
The deep subsurface is only going to be hotter than the surface. Um, Basic property of thermal physics of planets is that they're hot in the interior and cooler in the exterior. And even a planet like Venus with such a hot atmosphere, we expect there to be a geotherm or a veneerotherm that, there's no good physics that tells us there should be a cooler layer beneath the surface. So unless we're talking about some, science fictional exotic life that doesn't use water and carbon, which, we can't entirely rule out. But in terms of life as we know it, I don't think you can appeal to the subsurface on Venus.
A question from Gabriele. Is it possible to suppose the presence of a sulfur-based life on Venus in the clouds or in the deep subsurface of the planet?
Yeah, I'm very fond of sulfur as a basis for for life elsewhere. And on Venus in particular, we know there's a lot of interesting sulfur chemistry on Venus. And in fact, in some ways, sulfur is almost the carbon of Venus, if you will, and that, on Earth, you have this carbon cycle affecting the climate and coming out of volcanoes and being weathered and doing things in the clouds. And on Venus, we know we have sulfur, we think we have sulfur outgassing and forming cloud materials and doing complex things with photochemistry, forming unknown compounds in the clouds, maybe affecting this or creating this unknown ultraviolet absorber, and then also interacting with surface minerals and buffering the climate in various ways in the surface, and probably in the long run recycling into the interior. Sulfur is doing interesting things on Venus, and as I pointed out, a colleague and I many years ago wrote a paper about the possibility that sulfur could be supporting cloud-based life and acting as a sunscreen and so forth. Now, could you do that without carbon? That's a good question. I mean, I've often wondered about sulfur as a basis of life because it does form polymers in the long chain molecules. Now, they don't have all the properties that carbon polymers have, but maybe that's because we haven't studied them as much as we've studied carbon because we are carbon. So my view is that sulfur is worth further study as a possible basis for life, and it would be very interesting to know more about what sulfur is actually doing in those mode 3 cloud particles on Venus. Again, I don't think in the subsurface it's very likely unless you had a completely very radically different biochemistry that didn't need water or carbon at all. So I would put the probability of that very low, but not zero.